We're now entering the last topic that we look at in this course for advanced circuit analysis, and that's going to be two-port networks. But really, we define it as this black box right here. We have two terminals here, two terminals here. We just label them A, B, C, and D. And we have currents for A, B, C, and D. And we say we can have a two-port network if we can represent a circuit like this. And there's a few parameters that we need to concern ourselves with. That will be the admittance parameters, the impedance parameters, the hybrid parameters, and the transmission parameters. So the first one that we can look at is the admittance parameters. And really what we want to do is follow the equation where the current is equal to the admittance times the voltage. Or simply the admittance is equal to the current divided by the voltage. So we're going to set up a system of equations that looks like this, where we have our currents I1 and I2, our voltages V1 and V2, and then our admittance parameters given by this 2x2 matrix. So what this system of equations really tells us is that I1 is equal to Y11 times V1 plus Y12 times V2, and that I2 is equal to Y21 times V1 plus Y22 times V2. But we don't know any of these values for Y yet. And this is where we can apply a little trick to find out what these parameters are. Because we could say that if V1 is equal to 0, I1 is simply equal to Y12 times V2, and that I2 is equal to Y22 times V2. Similarly, if V2 is equal to 0, or short-circuited, say that I1 is equal to Y11 times V1, and I2 is equal to I21 times V1. Or we can simply set up each of the parameters like this, where we are either looking at V1 being shorted or V2 being shorted. And we can say that if the network has no dependent sources, Y12 is equal to Y21, and we can simplify the network into this pi equivalent circuit. So what this looks like is the following, where we simply have three elements. We have on the left here Y11 plus Y12. In the middle, we have minus Y12. And on the right, we have Y22 plus Y12. But if our circuit does have dependent sources, then we get something that looks like this, where we have to model these dependent sources. Not crazy to work with, but just something to keep note of. So if we consider an example where we have a circuit that looks like this, where you can see that we do have a dependent source, so we can't use that pi equivalent circuit. But we know how to find all of the parameters for the admittance. So the first thing that we can do is simply short V1 or set V1 equal to 0. And if we do that and we keep the current like this, we can look at a node Vx and do a nodal analysis. So if we look at that node Vx, we can say that I1 is going in right here. And then coming out of that node, we have the dependent source 2I1. We have some current Vx divided by this 2 ohm resistor right here. And then we have an additional current where we have Vx minus V2 divided by 4 ohms. And we can label the current like this, because we do have an additional node right here for which we label I2 as we need to. So we can also express I1 simply as 0 minus Vx divided by this 8 ohm resistor. And we can plug this value into our nodal equation above to arrive at this term here. And we can rearrange things simply to have V2 isolated. And the reason we do this is simply because Y12 is equal to I1 divided by V2 when V1 is shorted. And we know what I1 is from up here. We had that in terms of Vx. And we just arrived at V2 in terms of Vx. So we can plug those in. And we have a cancellation of the Vx's. We're just left at this term here. Similarly, we can find Y22 by I2 divided by V2 when V1 is shorted. And simply looking at that second node, we can say that I2 is equal to this term here. We can plug in what we already know for I1 and V2 in terms of Vx to arrive at this pretty annoying term here, but it is what it is. And simply we can divide I2 by V2 to get what Y22 is equal to. A little bit messy to work with, but we get the cancellation of Vx's. We're simply left with just numbers so we can get a value. Now looking at the other side, we're simply going to short V2. And we know the conditions we are looking for will be Y11 and Y21. And we can do a similar nodal analysis. And what we get is that Y11 is equal to 0.15 Siemens and Y21 is equal to minus 0.25 Siemens. So we can take our parameters for the admittance and simply plug them in. And now we can relate the current and the voltages with the admittance parameters. Now we also have impedance parameters where we're going to try to set up the equation that V is equal to Z times I. So what we get here is another system of equations where we have our Z parameters and we can find what those Z parameters are. And again, if a network has no dependent sources, we say that Z12 is equal to Z21, and we can simplify the network again, but instead of a pi equivalent circuit, we get a T equivalent circuit. So what that looks like is the following, where here on the left, you have the T equivalent circuit, but here on the right, if you have dependent sources in the network, you have to model them like this. So we can consider this example where we have this circuit here on the left. You can see that we have either I2 equal to 0 or I1 being equal to 0, which would mean that we have an open circuit on those terminals, either V1 or V2. So first, we're going to set I1 equal to 0, so we have an open circuit, and we can clean up this circuit a little bit by combining the two 80 ohm resistors here in parallel. So our circuit looks like this, and what we're going to be looking for is Z12, which is equal to V1 divided by I2, when I1 is equal to 0. And we know that if we have an open circuit at V1, no current flows through this 20 ohm resistor, but V1 is simply equal to the voltage divider over that 40 ohm. So we have V1 being equal to V2 times 40 divided by 40 plus 30. And then for I2, that's simply going to be equal to V2 divided by 70. And then Z22 simply going to be equal to V2 divided by I2 when I1 is equal to 0, which is going to be equal to V2 divided by V2 divided by 70. So those are pretty easy to evaluate because the V2s cancel out and it's just real numbers to work with. And now if we look at the other side where we set I2 being equal to 0, again, this current is equal to 0, so there's no current through this 30 ohm. We're looking for Z21, which is equal to V2 divided by I1 when I2 is equal to 0. That's going to be equal to V1 times 40 divided by 40 plus 20 divided by I1, which is going to be equal to V1 divided by 60. Again, the sum of the 20 ohm and the 40 ohm. And then Z11 is simply equal to, scroll up a little bit to see it, V1 divided by I1 when I2 is equal to 0. Again, the V1s cancel out, and it's just working with real numbers here. So from all of this, we end up with the following impedance parameters, 60-40, 40-70. And if you notice, this system was originally a T equivalent circuit. And if you plug in the parameters up here into this T equivalent circuit for these impedances, you'll notice that you should get the same values.